But give me some outcomes for 4 coins. What could you get?
All tails.
All heads, all tails? All heads, all tails.
2 heads, 2 tails.
Two of each, right? 2 heads, 2 tails.
3 tails, 1 head.
3 tails. I heard both of them. Thank you guys. 3 heads, 1 tail, or 3 tails, 1 head. That's pretty much it, right? That's pretty much it. I mean, that's what you can either get: all heads, 3 heads, 2 heads, 1 heads, or no heads. I mean, hopefully that breaks down to what you could actually get. So I'm going to give you guys Sean theory. Oh, Rob, ask me that question.
No question.
Okay, you sure? That was okay. Good. Let's do. Sean's theory is the probability of all these things is therefore 1 in 5. Hold that thought. What's wrong with Sean's theory?
There's 16 different combinations.
You guys don't want to hold that. Good. So, but wait a minute. There's only 5 events.
But there's 16 possibilities.
But there's only 5 events.
But you could rearrange them.
I could. But there'll still be 5 if I move them around.
There's more ways.
I think when you say the word them, Natasha, I'm thinking of a different word them. I hear what you're saying. My point is that there are 5 events, but you guys are claiming that there are more than 5 elements.
3 events more often.
Boom! That's what I needed to hear. There are only 5 events, but these events are not equally likely. That's the problem with the classical approach, forcing it into a situation where it shouldn't be forced. I'm not saying we can't use the classical approach on this. I'm saying we shouldn't use it right here. Now, before we go into the breakdown of the sample space, both these ladies up here figured out there are 16 items in it. And there are. And that, I think, was one of your project results. I do want to end with that. If we don't end with it, we'll bring it into the next class. Let's collect some data. How many of you got all heads? How many times did we actually see 4 heads in a row? 4 heads in a row. So you went flip, 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 and they were all heads. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. Let's put that in red. 16. All tailed. All tails. 1, 2, 3, 4, 5, 6, 7, 8. Two of each. 2 of each. 2 heads and 2 tails. Ah, the 2 hands come up for some of these. Yes, the 2 hands come up. So obviously, if you see my 1/5 is out the window. Seeing lots of 2 hands come up. Right, 1, 2, 3, 4, 5, 6. It's 12, 13, 14, 16, 17, 24, 26, 31, 31 plus 6 is 37, 43, 48, 52, 56, 57, 63. Well, yeah, Sean is wrong. Sean is wrong. How about 3 heads and 1 tail? 3 heads and 1 tail. 2 hands back up again. I love it. 3 heads and 1 tail. I don't care about the order. Just care about the numbers. 1, 2, 3, 6, 10. Shells, that's 4, right? 14, 22, it's all good, 22, mine either, it's broken. 22, shoot, I lost count. 6, I thought I had it. I was holding on to it. I said the one extra statement that kicked it out, ADD. 6, 10, 14, 16, 22, 20, plus 4 is 26, 29, 34, 37, 44, 45, 46, 47, 51, 55. Now, if I did this right, I should be able to calculate what the last one is. Chances are I didn't. So let's just have you guys tell me. 3 tails and 1 head. 3 tails and 1 head. 11, 13, 16, 19, 20, 21, 24, 27, 28, 32, 34, 37, 39, 46, 48. All right. Theoretically, let's see how I did. Let's see how close I got to 190. 24, 87, 132, 180. That is. Check that math. At least it ends in 0. I should have gotten more excited about it.
190.
Is that 190?
Yeah.
Holy hell! I forgot to carry. Jesus.
Wow.
YouTube world, you see that?
We won't say anything if you will.
Well, I just did. I'm gonna brag about this. I actually added correctly. Well, no, I shouldn't say that. Either added correctly or uniformly screwed up. Theoretically, I'll tell you what. Let's do this. I'm gonna leave this as bring this for next time. I'm gonna give you some homework, which I don't often do outside of quizzes. Figure this out. Two things. Number one, based on these numbers we just got, calculate the empirical probabilities of each of these five things. So what's the empirical probability of all heads, all tails, 2 of each, 3 and 1, and 1 and 3? Remember how we did that? Just
16 divided by 1.
exactly. That divided by that divided by that, all the way down. Then figure out the theoretical. Now that you're going to have to figure the sample space out for, right? You have to figure out how many ways you can have the 4 coins fall. And you guys already figured there are 16 ways. So the theoretical is going to be out of 16. That's your guys, you have to figure that out, kind of sit through, draw tree diagrams if you have to. Your last project probably has it still uploaded on the web so you can see it if you need it there. Okay, and we'll start with that and then we'll move to dice next time. I apologize, no time for dice today, but go ahead and return the coins and the dice. It's like a new thing, doesn't it?
It is.
That is a new one, it's snuck in.
2013.
2013. We'll throw that one back in there. Thank you guys. Dice probabilities on.
16 and 8?
Say that again.
Did
There.
I say 16 and 8?
16 and 8, yes ma'am. Kind of weird, huh? But, again, small sample size, high volatility. We'll let this thing play. I actually have a simulation we didn't get to. I'll play it with it next time. The simulation, you'll see how it evens out pretty nicely over time. Cool? Yeah, good stuff, dude. Good stuff. Good stuff. Thank you guys. Have a good rest of your day. I can't believe I got it right. Let's just look at that again. Let's just zoom in on that 190. Yeah, look at that. Rule adds for the first time ever correctly. Woo!